And let's see, as for announcements, I guess there's just a reminder that homework is due today. And I'm going to post some solutions to it. So it's 7.1 that's due today. I give an extra 24 hours after the due date for students that were late getting it in on time. And then after that, so I guess Friday morning, I'll post the solutions to it. And I left the regrade window on the midterms open until Friday. So just a reminder about that. If you haven't already checked out your midterm and requested regrades. Okay, so hopefully you all watched the video that I already posted. In fact, let me just ask. How many of you watched the video? Can you just say yes or no? Okay, cool. So yeah, most of you did. So then there's just 3 examples that I had. One about fusilli and one about a torus or donut, which is actually a 2-part example. Any questions before I start getting into all that? Like maybe any questions on the lecture, for example. I was talking about surface area. I gave the surface area formula, which is this one. I also gave 2 special case formulas. Well, 3 special case formulas, which is this one for a graph, this one for a surface of revolution, and this one, which is also for a surface of revolution. Okay, so if there aren't any questions on that, then I'll do the first example, which was about fusilli, which is a type of pasta. It's basically like an egg noodle. There's some egg noodles actually, which look more or less like the surface that I would like to calculate the surface area of. And there's a plot of it in MATLAB. Or maybe that's math. It's like Mathematica actually. So the plan is to compute the surface area of this noodle, and our formula will be the surface area formula. So I better first calculate the tangents, and then calculate the normal, and then, well, take its norm and integrate it. So let's proceed. If this is my parameterization, then my 2 tangents are TU, which apparently will be cos V, sine V, 0, and TV, which will be negative U sine V, U cos V, 1. And you could visualize the 2 tangents on the picture there. Let's see. TU points something like that, and TV points something like that. So their normal vector is going to be something like that. Let's compute the normal vector. It's TU cross TV. So write that out. Let's see. Cos V, sine V, 0. Negative U sine V, U cos V, 1. Oh yeah, I'll still upload this recording. Okay. So yes, hopefully you remember how to take a cross product. If you're rusty on your cross products, then those are included in the set of review problems, in the review problem set that's on the homework page for this class. So I would recommend going back and reviewing those as necessary. In this case, I get I hat times sine v minus 0 plus j, or maybe minus j hat times cos v plus k hat times u cos squared v minus minus is plus u sine squared v. So sine v negative cos v. Oh, this is just u. Having computed my normal vector, I should find its length now. The length of the normal vector, right? And this is what I'm going to be integrating to find area. Currently, this is going to be sine squared plus cos squared plus u squared, or 1 plus u squared. So I found the length of my normal. And now I guess I better just integrate that over the range of u and v. You look at the parameterization, u and v are in this set right here. By the way, someone asked me a good question last class, which is, how do you know what the surface looks like given a parameterization? And yeah, that's potentially a tough question. Like, you could, in theory, see one that would be really hard, although in practice, you're not really going to be asked to come up with a hard one yourself. If you think about the exam, I actually put pictures of all the surfaces that were even potentially hard to figure out. I included their picture on the exam, so like that wouldn't have been an issue, hopefully. Krishna asked if these are polar coordinates. Kind of close. You'll notice, yeah, this the z component here changes with the angle, which is a little bit different. So they're related. Apparently, like the angle that this thing is twisted at is one of the parameters. It can be kind of hard to give a or to generalize like a physical interpretation of what the parameters u and v are. But even if you don't have one, you can still just proceed to do the calculation automatically. Oh, thanks, Martha. V. And Krishna asked, why use u and v if it's cylindrical? Well, u and v were the coordinates that I was given the parameterization in. So I'm just using the ones that were given. You can use any letter you want. U and v are common ones. Sometimes S and P, R and theta. So since u is given to be in -1, 1, and v is given to be in 0 to 2 pi, the area formula states that the area of S will be the integral from 0 to 2 pi and from -1 to 1 of, well, the length of our norm, that is 1 plus u squared. So at this point, we just have a double integral problem. Although, if you've tried this problem already, it ends up being kind of tricky unless you use a table. So V does not even appear, so that one is easy to compute. Tell me if this is a true equation. Yes or no, folks? Is that a true equation? Oh, nice. Yes, that is true. Yes, because 1 plus u squared is even, and the integral is symmetric. Okay, so this integral is kind of hard, so I'm just going to use a table to compute it. Let me show you the formula, which can be found in the back of your textbook where it has a table of integrals. This is the entry that you'll find on the table of integrals in your textbook. Also, of course, you could use like software, to do this instead, but I'm keeping it old school. So comparing this integrand to the table, we see that A is 1, and we're dealing with the positive option. So I get 4 pi times u over 2, the square root of 1 plus u squared plus 1/2 times ln of u plus square root of u squared plus 1, evaluated from 0 to 1, is 4 pi times 1/2 times root 2 times 1/2 the ln of 1 plus root 2. And when you plug in 0, you get 0. I'll just say -0. So my final answer is 2 pi times root 2 plus ln 1 plus root 2. Any questions on this one? Okay, then let's try the donut. So some of the other formulas that I gave in the lecture are for surfaces of revolution. And also graphs. So there's all these different surface formulas. Usually, if one of them applies, that's probably the one you want to use. So here's the problem with the torus. Here we have a torus with a big radius of capital R and like a little radius of 1. And we want to compute its surface area. And there's more than one way you could do it. One way would be to proceed directly using the first surface area formula where you compute TU and TB. And this one's kind of a pain if you do all the calculations. Like here, I'll tell you, for example, what your tangent vectors would be. Let's see, T theta would be one of them. That's like negative R, or sorry, T phi. Let me do T phi first. T phi would be one of them. I guess that would be negative sine phi cos theta, negative sine phi sine theta, and cosine phi. That would be one of your tangents. Your other one would be, let's see, theta is R plus cos sine theta, and R plus cos phi cos theta, 0. You can see this problem's already looking fun. I don't want to actually do the computation of the normal. Right, like n, which is b cross t theta. How about I'll just tell you what the answer is, because doing the cross product and the determinant, it takes a while. So I'll leave that for you to verify, and I'll just tell you that the result is that n is R plus cos phi cos theta, R plus cos phi sine theta, and negative R plus cos phi sine phi. Yeah, because I've already worked this out, so you can verify that for yourself. Krishna asked if we could do this by rotating it around the z-axis. Yes, so that's the second part of this example. In fact, asks you to perform the same error or calculate the area using that interpretation. Anyway, with this being the normal, its length ends up being, again, this is something that you can check because it's a lot of algebra, so I won't show it here. But we just end up with actually just R plus cosine of phi. Kind of nice, simple normal. So the area of the torus will be, let's look at the bounds. I think they're both from 0 to 2 pi. Yes, they are. Both theta and phi go from 0 to 2 pi. So I get 2 pi R times theta sine theta, no, sine phi, sorry, R times T. Like the sign term disappears when we evaluate it at the endpoint. So there's our answer. Notice, by the way, you could write it as 2 times pi times 1 and 2 times pi times r. Like it's the product of the circumference of the little circle and the circumference of the big one. Oh, Dimitri said this reminds you of spherical coordinates. Yes, excellent point. So this actually is a coordinate system. There is a such thing as, they call it toroidal coordinates, I think, and it looks a lot like this. Yeah, good. So good point. That would be yet another curvilinear coordinate system. So here's the answer. And the last challenge was to try to do this as a surface of revolution. So to do the same problem as a surface of revolution, I'm just going to use the top half. So imagine, slicing a bagel like you're going to put it in a toaster. I'll compute the surface area of the top half and double it, which means I need this function right there. It's the upper half of a circle centered at R and of radius 1. So that means that this point is R plus 1, and this point is R minus 1. And you can use the equation of a circle to verify that that's where Z is equal to the square root of 1 minus x minus r squared. So that's like my f of x in the surface of revolution formula. So any questions on how I got the function that I want to revolve? Well, let me know if you have a question. I'll just start doing the computation now. So with that as my f, I'm going to need to know what f prime is. It's 1/2, 1 minus x minus r squared to the negative 1/2 times 2 times x minus r. Actually, maybe there's a negative sign, although the negative sign is going to disappear. So now I'm ready to. Oh, someone was asking how I found f. I found f because this was a circle. Here, let me draw it in another color. How about in blue? This is a circle centered at Imagine that we're in the xz plane. So I'll say it's centered at xz equals r comma 0. Namely, it's centered at this point right there, end of radius 1. So you have to remember the circle formula, which is that I should say you have to remember the formula of a circle that's centered at some point in the plane, which is not the origin. And that formula is x minus r squared plus, in this case, z minus 0 squared equals 1 squared. And then I solve that for z to get the top half. Cool. Okay. So I now want to use the formula. Let me just show you the formula I want to use real fast. This one. Okay. So plugging that into that formula, I'll have that the area of the torus is, I'm going to stick a 2 since we're only doing the upper half. Okay. So this 2 is for the upper half. So I need to double my answer. And then the formula is 2 pi times the integral of the function over the interval it's defined on. In this case, it goes from r minus 1 to r plus 1. And according to the formula, which I apologize, it's off screen right now, I then need the square root of 1 plus f prime squared. Okay, so this term is f prime squared. This term is just x because x is positive. So we get 4 pi the integral r minus 1 to r plus 1 of x times 1 plus x minus r squared over 1 minus x minus r squared. All under a square root sign dx. This can be simplified, by the way. It's just 1 over 1 minus x minus r squared. So I get 4 pi the integral from r minus 1 to r plus 1 of, after taking the square root, it's x over the square root of 1 minus x minus r squared. Okay, we're making progress. I think it'll be easier to do a substitution. How about I let w equal x minus r. So x is r plus w, dx is dw. When x is r minus 1, w is -1. And when x is r plus 1, w is +1. I'm just converting everything. I want this term to just be w. So in terms of w now, my new limits are now -1 to 1, which is nicer limits. In terms of w, x is w plus r. Okay. So after the substitution, this is what I've got a question. Why is it only a single integral? So yeah, like this is a surface area. Shouldn't it be a double integral? The thing about surfaces of revolution, surfaces of revolution have a high degree of symmetry in them. So they're kind of like halfway between something being one-dimensional and two-dimensional. So you're basically asking where this formula comes from. And I could show you, the book talks a bit about it as well. I probably shouldn't try to right now, but I can talk a bit more about it after I finish the example. So here's a yes or no question for you all. This is a good one too. I want you to tell me if these are equal or not. Okay. Is that a true equation? Yes or no? It looks like I just dropped one of the, just dropped the W. Just got rid of it. Did I do that? I mean, it'd be kind of nice if I could. Any reason why I could just drop this W? You could do that if the integral of that term was 0. If it was odd. Yeah. So W over square root 1 minus W squared is odd. So that's why we can't. So the answer is yes. Yes, we can, because this is an odd function. So I just drop that term. And I'm really left with this trig integral. I could write it as, let's see, let me do another substitution. So let's let W equal sine t. dw is cos t dt. At W equals -1, t is -pi over 2. And if W equals 1, t is positive pi over 2. So with that, and let's pull the r up in front. 4 pi r times the integral of negative pi over 2 pi over 2. With this substitution, the denominator becomes cosine of t after making this trig substitution. So I'll get a cosine of t. dw is cos t dt. Cosines cancel. So I get 4 pi r times t from negative pi over 2 to pi over 2, which is 4 pi r times pi, which I really hope is the same answer as last time. 4 pi squared r. Is that the same answer as last time? Yeah, 4 pi squared r. 4 pi squared r. Yes. All right. Good. I got this thing. Oh, there's a question about why I could drop the w. It's because the integral was 0. So if you integrate an odd function over a symmetric region, you get 0. And that's why that integral was 0. So like w wasn't 0, but the integral of that term is 0. In general, if you integrate negative a to a g of t dt, you get 0 if g is off. So yeah, that's it. Just had these 3 like heavy duty calculations today. These are intense, by the way. Like I didn't give easy problems here. These are tough ones. Some of the heavier duty calculations in this class, actually. Cool. Yeah, so that's it, folks. I'll hang out and answer questions. Please stick around if you do have questions. That's the point. And to everyone else, I'll see you all Friday. Oh, yeah, Daniel wants to see the equation. Yeah. These ones. And by the way, they're all in the notes. I actually posted the notes before class, and then I'll also post these as well now that I've completed them. Oh yeah, Krishna noticed that the axes were different. So this formula, it was kind of arbitrary that I labeled the vertical axis as y. You could have that axis have any name that you want. In the problem where I applied the formula, it ended up being that the vertical axis was called the z-axis at that time. So you could rewrite this where this is a z and this is a z and this is a z if you wanted. It's kind of arbitrary. The point was I was rotating a function of one of the axes around the other axis. And that's when this is the appropriate formula. One of the ways that you can remember which formula to use is they should have like a 2 pi r term. This comes from the Shell's formula, which you may have learned in calculus, right? Like volumes by shells has a 2 pi r term. And in this case, r is your x value. Right? There's like your radius r. So that's why there's an x right there. But in this case, r is like the y value, which is f of x. So that's why there's an f of x term.
I'm sorry, you mind scrolling up a bit more so I can see the description of the first one? Thank you.
Mhm. Oh, there's a question about proving these. Yeah. I thought you'd never ask. Yes, you can prove these. So, like for example, how would you prove the graph formula? So if z is f of x, y, what's your surface area element? I mean, I guess first you could find your two tangents. So check this out. If S is defined by Z being some function of X and Y. So it's like X and Y live in some domain, and then your surface is some surface that's on top of the domain. In order to come up with our formulas, we've needed a parameterization. Can you think of a parameterization for this surface? It has a built-in, here's a hint, there's a built-in parameterization. Ah, good, yes, exactly, in terms of X and Y, good. So X, Y, f of X, Y, that's a parameterization. That's like your phi of X and Y if you want. So yeah, just use that and then start plugging and chugging in the formulas. Like your tangent vector in the X direction apparently will be 1, 0, df dx. Your tangent vector in the Y direction will be 0, 1, df dy. Your normal vector will be the determinant of 1, 0, df dx, 0, 1, df dy, which is, let's see, what is that? Df dx. Df dy, or negative df dy. Oh, minus, there's a minus. Minus df dx. minus df dy and 1. So the norm of n ends up being df dx squared, df dy squared, and 1 squared. Oh, and then that gives the formula, which is right there. Yeah, so that produces that. All right, let's see, Martha was asking. Okay, let's see. So for surfaces of revolution, I think you can. There's more than one way. Here might be one way. I'm not sure if this will work because I haven't tried this, but let's say that there's your function. I can use z or y for the vertical axis. I'll just leave it as z. How about it? Doesn't matter. Let's say z is a function of x, single variable function of x. Check this out. If we pick a small piece of that path, approximately, what's the length of that small little, I'll explain where the 2 pi comes from in a second. Here's a hint. It's going to be the area of a so-called frustrum, which is like a part of a cone. It's kind of like what you put on your dog when he gets neutered, after he gets neutered or has surgery. So it all starts by approximating a little piece of this path by a straight line segment. Yeah, you use arc length. And if I zoom in on this, I can draw a little triangle where the height of it is here, where the bottom side is, let's say, dx. The height is delta, I guess I'm using z, but it's approximately f prime of x delta x. So we've got a little right triangle right here. This little right triangle has hypotenuse approximately square root of delta x squared plus f prime of x delta x squared. So that's our like infinitesimal path length element. Now go to the frustrum and suppose, oh, and let me simplify that a little bit. I can pull out the delta x and it becomes 1 plus f prime of x quantity squared and then a delta x outside the square root. So that's this length right here. This thing has length 1 plus f prime of x squared delta x. Yeah, that's where the 1 comes from. I'm trying to remember what the area of a frustrum is. I think it's 2 pi times the radius times the height. So like if this distance is r, which in the picture, by the way, the distance is f of x. So r is like f of x, if we're rotating around the x-axis for this problem. And if you look up, say, the surface area of a frustrum, let's see. Frustrum. Frustrum area. I think you have to do like a little approximation. Okay, so there's a little bit of work that I'm kind of skipping over, which is justifying the following. So I claim the area of this thing, the surface area of this frustrum, is approximately 2 pi times the radius times the length. So that would be 2 pi times f of x times 1 plus f prime of x squared delta x. So then you split the entire region into a whole bunch of frustrums and just add up all of those. Add them all up. So the area is sum of 2 pi f of x times each of those. And in the limit that you let the delta x get very small, you get exactly the formula for the surface area. Now I could justify this part right here. Although there's also another way to do this problem, and that's using the previous surface area formula and also polar coordinates. And that's what the book does. So you'll notice, I believe, if I'm remembering correctly, that the book also answered your question, but they do it differently. And they use, I think, if I'm remembering, they use polar coordinates. So you can also derive this in a different way, which is kind of neat. And yeah, you can see that it ends up just being an integral of one variable, because this is kind of a one variable problem, kind of. there's so much symmetry that it can be reduced to a one variable. So yeah, you're welcome. I'm sorry, there's probably more than you thought you might be asking for, but as you can see, I kind of like this stuff.